Hello everyone, thank you for visiting my channel. This is Joe here, Joe Daoud, and in today's video I received a question from a student regarding binomial expansion. So in the binomial expansions, I'm going to go through the question with you and show you the steps. So the question was 1 minus sine squared x to the power of 3. Now in binomial expansions, whenever we have a process of expanding binomials, we can use the Pascal's triangle. And in Pascal's triangle, we start off with creating like a branch system of expansion. From the branch system of expansion, we generate then the coefficients we would see in a typical expansion of the binomial to the power of n. So whether it's a binomial to the power of 2, 3, 4, 5, we can the Pascal's triangle gives us exact coefficients that are required for each a number to the power, each power n. So I'll go over quickly the Pascal's triangle. So in the Pascal's triangle, we're going to start off with the 1, and as I'll write that out, Pascal's triangle. Okay. So we start off with the 1 at the top. And then the second row is a 1 and a 1. And then in the third row, what we're doing here is we're writing always on the boundaries, on the exterior outer limits, 1, and then we add the numbers at the top in the row above it. So if you notice, there was a 1, and then I created a 2. So that 2, where did that come about? Is the addition of the two numbers in the previous row that are sort of connecting with the 2 to make a triangle. So you have a 1, 1, 1 plus 1 is 2, and then always in the outer limits of binomial triangle, and then Pascal's triangle is a 1. So we can continue. So again, you would see then you would generate the fourth row would be a 1, and then 2 plus 1 is 3, then again 2 plus 1 is 3, and then again the outside boundary is a 1. So we can continue. Now we know that the starting row is n equals 0, so that's when your power is 0. The second row would be n equals 1, the third row would be n equals 2, and then the fourth row would be n equals to 3. So we're going to be using the fourth row, which represents n to the power n equals to the 3, which is the binomial to the power of 3. So I'm going to start off with writing out the coefficients. So as we said, the Pascal's triangle gives us the exact coefficients we would see in the binomial when it's expanded. So I'm just showing you here when you go to the fifth row, which is n equals 4, you would end up seeing coefficients in each section 1, 4, 6, 4, 1. In that pattern, you would see that throughout all of Pascal's triangle. Pascal's triangle is used a lot, not only in binomial expansions, but you would see that in vectors and in vector calculus, and you would also see that in a variety of other mathematical equations. Technically, you see that in high school you would only see it in terms of a binomial expansions, but there is calculations related to parametric calculus, parametric values, and yeah, so in this context we write out the coefficients, so 1, 3, 3, 1. Now I'm including parentheses. So the pattern, you see that because you have two terms in the binomial, each parentheses for each coefficient represents the first and second term. And what you start off with is in the first term, you see the first term is always going to be raised to the power of the exponent of the binomial. So if your binomial is to the power of 3, your first term is always going to be raised to the power of 3. So again, in the binomial there's two terms, the first and second, or a and b, as I described here. And each coefficient is followed by a first and a second term, which is found in the binomial. The first term is always to the power of 3, and the second term is always to the power of 0. So as you see here, I'm just labeling the powers. So the first term is going to be to the power of 3, and then subsequently it starts to go down in this from the second set of from the second coefficient. So when you have the coefficient of 3, you would have the first term to the power of 2, and then again in the third section another coefficient to the power of coefficient 3. The first term would be to the power of 1, and you see that pattern 3, 2, 1, 0. The second term is the opposite. So the second term is to start off with 0, and then you're gonna incrementally go up to the power that you have in your binomial, which is in this case 3. So you go up from 0. The second would be 1, 2, and 3. What I'm going to do next is I'm just going to fill in each parentheses by its specific term. So the first one is going to be the first term, and the second parenthesis in it is going to be the second term. So my first term is 1. My second term in the binomial is negative sine squared x. So in each parentheses, I'm going to replace them subsequently by the first and second terms. In between each coefficient, we're going to, and set of values, we're going to put a plus sign. So I will include that. And once you come to this part of the equation, it becomes relatively easy to expand. The reason is you have everything set up for you. You have included everything. Usually these equations are not that difficult. It gets confusing if you try to solve everything at once and try to keep this all in your head and try to implement it. But if you follow a system like this using Pascal's triangle, it becomes relatively easy. So what we're going to do next is we're going to start off with 1 times 1 to the power of 3 is 1, and then negative sine squared x to the power of 0, anything to the power of 0 is 1. So in the first set of terms you have 1 times 1 times 1. Then we're going to put a plus sign, and now we're going to get to the second set. So 3 times, so I forgot to add the plus signs in between them, so I'm going to do that. So what we get next is 3 times 1 to the power of 2. Now 1 to the power of 2 is just 1. And then you have negative sine squared x to the power of 1. Okay, so we'll do that. Then the next set of terms, 3 times 1 to the power of 1 is 1, and then negative sine squared x to the power of 2. And then finally, in our last set of terms, we have the coefficient was 1, and then 1 to the power of 0 is just 1. So I'll just erase this here from the Pascal's triangle. And right, so then 1 to the power of, yeah, just fix the plus sign. So 1 to the power of 0 is 1, and then you end up having negative sine squared x to the power of 3. Okay, so we're getting somewhere now. It's sort of all free fall from here. It's not going to be that much more complicated. So 1 times 1 times 1 is 1. Now you're going to start expanding. So 3 times 1 is 3, and then you end up with 3. 3 times negative sine squared x is negative sine squared x. Because you have negative sine squared x, the negative goes, when you want to simplify, to the in front of the number. So you always want to put the signs in front of your numbers. So negative 3 sine squared x. The next set of terms, you have 3 times 1 times negative sine squared x to the power of 2. Anytime you have negative sine squared x to the power of 2, you're multiplying it together. So negative times negative gives you a positive, and sine squared x to the power of 2, you multiply 2 times 2 is 4. So you end up with plus sine to the power of 4x. Finally, in your last set of terms, you have 1 plus 1 times negative sine squared x to the power of 3. Now you have negative sine squared x to the power of 3. 3 is an odd number, and then your negative would remain. Negative times negative gives you a negative. So your final answer would be negative. And then sine squared x to the power of 3 is sine to the power of 6x. Okay. So this is a solution. This is a long answer solution. The reason why I did this here is because you can have multiple answers to the question. This expansion would give you a long result. A longer result. You would see this in some trigonometric identity questions. Now there is an alternative solution because of the nature of trigonometric identities, you can come to multiple solutions from one binomial raised to the power of n. You can have a variety of answers as well because of the trigonometric identities. This is a long solution. This is a correct solution, but this might not be the most simplified form. If the teacher is asking you for, let's say the question comes out and says, expand the binomial in its simplest form, or in one term. Expand, simplify into one term. So if they give you, for example, expand and simplify in the most simplest terms, what you're going to do is you're going to have to resort to Pythagorean identities. So if you go back to your advanced functions or algebra textbooks, you can look and find what the Pythagorean identity results. Very, very important one you should memorize. You should know what it is. It's sine squared x plus cos squared x equals 1. If you need to prove that, you may need to be asked to prove that. I can try to make another video in the future at some point of proving the Pythagorean identity. It's based on the unit circle. It's fairly easy to prove from a unit circle. So from this identity, sine squared x plus cos squared x equals 1, what we're going to look at is rearranging 1 minus sine squared x. Now 1 minus sine squared x, we can really easily rearrange this equation. We can move the sine squared x to the right side of the equation sign, so technically subtracting both sides by sine squared x. And doing this, you generate a simpler term, and that is that 1 minus sine squared x equals cos squared x. What we're going to do with cos squared x now is we're going to substitute our equation through a quick substitution. We're going to change the 1 minus sine squared x and substitute it with cos squared x, because we now prove that in our rearrangement of the Pythagorean identity. It's fairly simple. You just take that cos squared x and you're going to put it in place of the 1 minus sine squared x in your equation. So this is what I did. We're just going to move this over. Okay. Now, that's how you have to really approach the trigonometric functions. You have to keep sort of what equations are available that you can substitute, you can eliminate, rearrange. You have to look in those contexts. You have to be really familiar with what can be proved. Most of them are proved from the Pythagorean identity and from simpler other identities as well. So if you get into like cos 2x, sine 2x, tan 2x, those are all identities that can be proven from simpler terms. So as you see, I replaced the 1 minus sine squared x with cos squared x, and then you just have to expand cos squared x to the power of 3. Because it's raised to the power, you multiply the exponent. 3 times 2 is 6, so your final answer in this case would be cosine to the power of 6x. And this is your most simplest term. Thank you very much. If you have any questions, you can always comment, send me a comment in the video in the comment section below. You can subscribe, that would be great, to our channel. And I'll be posting more and more educational videos regarding math and science. If you have any specific questions, you can always send me an email. You can also comment in the comment section, ask your questions there. I will gladly make a video to help you guys be more avid in math. It just all takes practice, as well as an open mind and trying to rearrange, always trying different things to get to a common solution. Finding the fastest route is key here, and keeping your mind open, but not, you need to know both ways. Some people, they try to always get the shortcuts. You need to know how to get to answers in the fastest route possible, but also you need to have understanding, working knowledge of longer equations and solutions to problems in the longer method. That's always helpful to just give you some extra strength and speed. So yeah, again, if you guys want to subscribe to this channel, that'd be great, and share, like this video. Take care. Bye bye.